As many can attest, when you join the censored Earth community, you are given a new set of eyes. Now, I've studied Earth science before, but now that I've been given a new set of eyes, I'm going to go back and take another look and tell you what I see. This is Modern Earth Science Destroyed. Unit 1.2, Paths to Discovery, Scientific Methods.
Through research, scientists seek to explain natural phenomena and solve mysteries of the Earth. Over the years, the scientific community has developed organized, logical approaches to scientific research called scientific methods. Scientific methods are not a set of sequential steps that scientists invariably follow. Rather, they are guides to scientific problem solving.
Ooh, we have got to highlight that. I have so many people who contact me and get after me because they are upset because I don't always follow the scientific method verbatim. This highlight here represents my upbringing in saying that it's okay. They are guidelines. If anyone wants to argue that the textbook is wrong here, be my guest. Okay, state the problem.
Scientific inquiry often begins as a result of observation.
That sounds familiar. Here at the Earth Institute of Science, we take pride in building upon a foundation of observation.
Simply put, observation is using the senses of sight, touch, taste, hearing, and smell to gather information about the world. When you notice thunderclouds forming in the summer sky, that is an observation. So, too, is feeling the cool, smooth surface of polished marble or hearing the roar of rapids around the bend of a river. Observations often lead to questioning. What causes tornadoes to form? Why is oil found only in certain locations and not in others? What causes a river to change its course? Asking questions like these is one way of stating the problem to be investigated through scientific methods. One problem that has long puzzled scientists is the extinction of the dinosaurs. For more than 135 million years, these huge reptiles dominated the Earth. Then, about 65 million years ago, the dinosaurs and 3/4 of all the other species on the Earth died out. Scientists wondered what could have caused such a mass extinction. What I want to know is, where did these numbers even come from? I don't see any references anywhere.
Just so you know, this book doesn't even have an appendix. Come on, guys. Wikipedia does a better job than this. And here they claim 3/4 of all other animal species on Earth died out. We don't even know how many different species exist on the Earth today. People are still discovering new ones. Yet the authors here are claiming to know exactly how many different species existed on the Earth millions of years ago. That doesn't sound right to me. If that were the case, people shouldn't still be discovering new dinosaurs supposedly from those time periods. It is clear that the authors here are expressing their opinions and treating them as facts.
Yeah, that is a problem.
Oh, and let's not forget, here the book also referred to dinosaurs as huge reptiles. When I took ornithology, a class about the study of birds at Dixie State University, they really grilled it into us that birds did not evolve from dinosaurs. Birds are dinosaurs, and birds are not reptiles. If you would like to learn more about that, or argue against it, we have more information about that on our debate board. Please come check it out. Okay, gather information.
To investigate a problem such as the extinction of the dinosaurs, scientists gather information. An important means of gathering information is measurement. Measurement involves the comparison of some aspect of an object or phenomenon with a standard unit such as a meter, a Celsius degree, or a kilogram. For example, when you measure a rock and find that it is 20 centimeters long, you are comparing the length of the rock with a unit of measure, 1 centimeter. What other units of measure can you name? Accuracy and precision are important in scientific measurements. Accuracy refers to how close you are to being correct. Precision involves a unit of measurement. For example, a distance measured in millimeters is more precise than a distance measured in centimeters. Measurements can be very precise and yet be completely inaccurate.
I've got to say, measurement is one of the biggest things people criticize me about. Now hear me with this. I believe in taking measurements, but I don't believe in taking measurements for the sake of taking measurements.
What do you mean by that?
Well, I recently had an interview with MC Toon, wherein we had a discussion about his Scrunched Horizon experiment. Here he took a photo of some levels on the horizon. Next, he scrunched his photo, producing this image of a curved horizon. Please note how, yes, I acknowledge the curve I can see in this photo, as I really think any viewer can see and recognize that his horizon doesn't appear straight. Do I need to measure that to know that it's curved? No, that would be stating the obvious. It would be measuring it for the sake of measuring it, and I just don't see the point in doing that. Now, even though I do acknowledge the curvature I see here, please note that I do not believe this is the curvature of the Earth that we are looking at. If it were the curvature of the Earth, the same amount of curvature should be present throughout the entire photo. But it's not there. MC Toon, however, disagrees with me. He claims that there is the same amount of curvature throughout this entire photo. So let's state a problem here. We both disagree about whether this curvature is even or uneven. If it is even, that means we are looking at the curvature of the Earth. But if it's not even, that means we're not looking at the curvature of the Earth.
So that is step 1 in the scientific method. State the problem. Now we can move on to step 2.
In order to settle our problem, now I have a reason to measure the horizon. So that's what I'm going to do. Now, instead of scrunching it this time, I'm just going to measure it all out the way it is. So first, I'm just going to adjust the brightness and contrast here. Try and get that as accurate as possible so we can get it nice and sharp so we can get a good accurate measurement. So here I have measured out that first little bit to be just over 200 pixels. And as you can see, that is all flat within 2 pixels. Now let's continue on and measure the curve that we see within the 2 levels. We'll just adjust that brightness and contrast again here real quick. Okay. So here we go measuring it by hundreds. 100 pixels, 200 pixels, 300 pixels. Zoom in on that. We'll see here that it goes up, so our rate of curvature is 1 out of 300. Starting over, 100, 200, 300, but it's still straight, so we're going to continue on. 400, 500. Now it moves up. Now our new rate of curvature is 1 out of 513. All right, let's see if that changes. 100, 200, 300, 400, 500, that's where it's supposed to change, but here we can see it's straight. So we'll keep going. 600, 700, 800, 915, and that's when it makes the next jump. That's a much bigger number than it was before. Actually, this is a fraction, so the number is actually getting smaller, meaning we are seeing smaller amounts of curvature than we were before. All right, now, if we're going to measure the amount of curvature over here on the second beam, then we're going to have to do the brightness and contrast all over again because it gets kind of messy over there. But we'll go ahead and do that for you. All right, here's our second beam. All right, let's change that brightness and contrast here. All right. Now it's still a little messy, but it's okay. It's good enough. Just go through here and see what that looks like. Yep, I think we're good here. So you'll notice in the second beam here, I didn't draw out the numbers like I did before. It was unnecessary because, as you'll see, we can make it all the way across the second beam and the horizon stays within the 2 pixels. Therefore, we can tell that this is not the curvature of the Earth that we are looking at because the curvature is uneven throughout the entire photo, thus proving my point.
So there you do believe in doing measurements, you just don't like doing them when they are just stating the obvious.
Exactly.
Okay, let's continue. In the case of the dinosaurs, scientists examined the fossil record for clues to what happened 65 million years ago. They studied rock layers throughout the world that date from the time when the dinosaurs disappeared. The scientists discovered that in certain locations, these layers contained iridium, a substance that is uncommon in earth rocks but common in meteorites. Scientists then measured the amount of iridium in the rock layers. They found that the rock layers in these particular locations contained nearly 160 times the amount of iridium normally found in earth rocks. The scientists searched for an explanation that would relate the iridium measurements to the disappearance of the dinosaurs.
Scientists examined, scientists discovered, scientists found, scientists searched. Really? What scientists did all this? Here the book is making a bunch of scientists say arguments, but they are not making any references to any specific scientists. And what the authors are really teaching people here is don't look any further into it. Just take our word for it.
If a scientist says it, then it must be true, right?
I've said it once and I'll say it again. The authors of the book are teaching people to fall victim to genetic fallacies.
Mr. Sensible, bring me some cheese, and get me only the best if you please.
Great. Thanks, Kyle. Let's have a look at this book. Well, I did a little bit of digging and I found the book. It's still available on Amazon. Modern Earth Science, Student Edition 2002. Grade level 9 and up. Reading level 14 years. Kyle, this is not a heavyweight detailed scientific book. It's an introduction for teenagers.
Yes, we've had a few people make that observation on our debate board. They have tried to make an excuse for the book due to the book's audience. Essentially what they're saying is, oh well, the book is written for teenagers, therefore the rules of logic don't apply. No. Just no. The rules of logic should apply very much to every level of education. Public education needs to be better than this. Our future generations need better than this.
A lot of people are asking, why are we going after a high school textbook from 2002?
Well, as I said in the beginning, this series is all about allowing others to view the world through our eyes. I graduated high school back in 2006, so this represents the exact kind of textbook I would have read back in high school. I also picked a high school textbook because I saw it as the foundation that comes before a college textbook. Perhaps when we're done with this series, we'll do a follow-up series about the book Physical Geography, which is the book that I studied in college.
Perhaps we'll do that. All right, let's continue.
All right. Form a hypothesis.
Once a problem has been stated and information gathered, a scientist may propose a hypothesis, a possible explanation or a solution to the problem. A hypothesis is based on facts, which are often established through observation. For example, the scientists who discovered the iridium-laden rock layers proposed the meteorite impact hypothesis to explain the extinction of the dinosaurs.
It's just unfortunate that we can't see any of these observations that they're talking about, or even know about what specific scientists are talking about.
This hypothesis states about 65 million years ago, a giant meteorite crashed into the Earth. The impact of the collision raised enough dust to block out the sun's rays for many years. The Earth probably became colder, plant life began to die, and many animal species, including the dinosaurs, became extinct. As the dust settled over the Earth, it formed a layer of iridium-laden rock.
Test the hypothesis.
Once a hypothesis has been proposed, it should be tested. A hypothesis will not be accepted by the scientific community unless there is evidence to support it.
Therefore, we should not accept much of what we read in this book.
Yeah, they do not provide much evidence to support their claims. A hypothesis is tested by experimentation. An experiment is a scientific procedure carried out according to certain guidelines. An experiment enables scientists to test each variable that might prove or disprove the hypothesis. A variable is a factor in an experiment that can be changed. An experiment set up to test a variable is called a controlled experiment. To ensure that only one variable is tested in an experiment, scientists will also run a control. The control will have the same conditions as the experiment, except for the variable being tested. For example, to test the effects of sunlight on a green plant, a scientist will grow two identical plants. To control the experiment, the scientist would vary the amount of sunlight reaching one plant while keeping the amount of sunlight constant on the other plant. The scientist would then observe both plants and record the observations. What is the variable in this experiment? In the study of earth science, setting up controlled experiments to test a hypothesis is often difficult and sometimes impossible. The scientists studying the disappearance of the dinosaurs, for instance, cannot bombard the Earth with a giant meteorite to see if it produces life-threatening conditions.
What is science? Science is based on things that are testable, reproducible, and falsifiable. You're not going to believe this. In science, we always say that you make observations, you have a theory, you go make more observations, and it's a very, very tedious process. Wrong. Nobody that I know of in my field uses the so-called scientific method. In our field, it's by the seat of your pants. It's leaps of logic. It's guesswork.
Guesswork. Beware, guys, this is the kind of science they're talking about here.
Recently, however, scientists have developed computer models that enable them to test hypotheses by simulating certain conditions. For example, scientists have entered information into a computer about the possible climatic conditions during the period when the dinosaurs became extinct. They found that a dust cloud resulting from the collision of a meteorite 10 kilometers in diameter would have been sufficient to lower the Earth's temperature considerably. When experimentation is impossible, scientists often make more observations to gather evidence that will either support or discredit the hypothesis. The hypothesis is then tested by examining how well it fits or explains all known observations. To test the meteorite impact hypothesis further, scientists had to find additional evidence that the iridium in the rock layers on Earth had once come from meteorites. Scientists again examined the rock layers, and this time they found strangely deformed particles of the mineral quartz. Previously, this type of quartz has been found only near meteorite craters at nuclear testing sites and in moon rocks. Scientists concluded that such quartz particles could have only been produced by an extremely powerful explosion. The collision of the Earth with a huge meteorite, they reasoned, could have produced such an explosion.
Here the book claims this is a meteor crater in the northern Arizona desert. Now, if this is a meteor crater, my question for the authors here is, where's the meteor? It all seems to have vaporized on impact. Was it made of ice or something? And where's all the splash damage? I don't see any smaller craters around this one anywhere. This kind of reminds me of the argument about whether all the craters on the moon were caused by meteors or not. And it reminds me of the question, when did the Earth go to war with the moon and start launching meteors at it? State a conclusion.
After many experiments and observations, scientists generally reach conclusions regarding the correctness of the hypothesis being considered. Depending on how well the hypothesis fits the known facts, it may be accepted as stated, altered slightly, or discarded altogether. The fossil evidence for the meteorite impact hypothesis does not prove that a meteorite was responsible for the extinction of the dinosaurs.
I've got to agree with them there.
The evidence does show, however, that an abnormally high amount of meteorite dust reached the Earth at that time.
What evidence? They didn't show us any.
Thus, until new evidence is found or a better hypothesis is proposed, the meteorite impact hypothesis serves as one possible explanation of why the dinosaurs disappeared.
I think it's interesting how the fossilization process requires the animals to get buried in mud, but the book doesn't point to getting buried in mud as the cause of death. Well, that concludes Lesson 1.2. Although let's not forget this part about the internet. Do you want to go for a spin on the information highway? Do you want to venture to cyberspace and surf the net? Then take a trek on the internet, a powerful information system that brings the electronic frontier to your doorstep. The internet began as an experimental computer network created by the United States Department of Defense during the Cold War. Its purpose was to safeguard scientific and military research in the event of a nuclear attack. If one or two computing centers were lost, the remaining sites in the network would continue to process and communicate vital data. Today, the backbone of the internet consists of millions of host computers worldwide. At least 300 million computer users access these internet computers using ordinary phone lines or cable TV lines. Once connected, they're able to send and retrieve information around the world with just a few keystrokes or mouse clicks. Access to so much information makes the internet an exciting place for scientific research. From online photographs of earthquake damage to space shuttle experiments displayed in real time.
Look like you're in a studio, maybe in Omaha, Nebraska or something. The shot is so clear. Is this a hoax? Are you really in space still?
I don't know. We're going to have to do something for you.
I want to do it. I know. Oh, yeah, I can do that. Watch this. Is this a hoax? Are you really in space still?
The information on the internet is extremely current. Much of this information is difficult or impossible to find elsewhere. Yeah, I don't think I would have the views I have today were it not for the internet. The internet also makes scientific collaboration easier than ever before. That's what we do on our debate board. You should come check it out if you haven't seen it yet. For the cost of an internet subscription, anyone can quickly share research with an international audience. Various discussion groups and electronic email services help scientists stay informed about new discoveries and make valuable contacts with other professionals in their field. For the new user, there is online help available, as well as numerous books and magazines about the internet. Throughout this textbook, you'll find web addresses directing you to websites known as homepages. These homepages relate to specific earth science topics and contain links to other useful websites. It would just be nice if you could find some good supporting evidence in some of those links. Feel free to check those out. Unit 1.3 will be about the Big Bang and the redshift theory. I really look forward to it, and I hope you'll join us then.
Thank you for watching.